What if I told you trigonometry isn't about triangles? No one said, I really want to find the ratios between any two sides of a right triangle. The foundations were laid thousands of years ago, in 2nd century BCE Greece, when a man named Hipparchus was obsessed with the movement of the heavens. He observed that everything in the sky, the sun, moon, planets, and stars, all followed a pattern. And if their motion followed patterns, then he could predict where any celestial body could be. Aristotle, who came before Hipparchus, believed that the universe was made up of layered spheres, with the Earth at the center and the sun, moon, and planets embedded in those spheres. And all the stars were thought to be part of the farthest sphere. This is important because it influenced Hipparchus' approach to predicting planetary motion. He simplified that spherical model into perfect circles, what we would now call orbits. Now, imagine Hipparchus wanted to track the motion of some planet, and he sees it move across the sky from, say, this point, we'll call it P1, all the way to P2. He sees it trace a path along the perfectly spherical dome of the sky. And with the initial and final position, he can calculate the angle it moved across the sky. So this angle here. Now, with this angle here, he actually wanted to find the straight line distance between these 2 points. This straight line distance is called a chord. Now, you might be wondering, if you wanted to track planetary motion, wouldn't it make more sense to find the arc length? Well, yes, but in those days, curves were very hard to work with geometrically. And astronomy was all about lines of sight, which were, as you can see, straight. So Hipparchus found it easier and more intuitive to find the chord length. The question now is, how can you find the chord length for any given angle? No one knows for certain who first proposed the methods to solve this problem. They likely emerged sometime during or after the era of Hipparchus, as Greek astronomers began needing more and more precise ways to predict the motion of celestial bodies. 2 geometric ideas appear to have become standard tools. The first was inscribing regular polygons inside a circle. Here I have a square inscribed in a circle. Now I can split the square up into 4 triangles by just drawing diagonals like this. Since these diagonals are perpendicular, the central angles for each of the triangles formed here is actually 90 degrees, a right angle. And the half diagonal lengths, so from a point on the circumference to the center, is equal to the radius. So we have 2 side lengths that are equal to the radius. So with this information, we can actually find the unknown side by using the Pythagorean theorem. And that gives us r times the square root of 2. But what's the meaning of this? Well, we just found the chord length of 90 degrees to be equal to r root 2. We can do the same thing with the hexagon. So here I'll just draw one triangle from adjacent vertices. And we still know that these 2 sides are equal to r, or the radius, because a line from the point in the circumference to the center is equal to the radius. And we also know that this angle here, the central angle, is 60 degrees. If you have an isosceles triangle, a triangle with 2 equal side lengths, and a central angle, the angle between them, of 60 degrees, that triangle must be an equilateral triangle. So all the other angles are also equal to 60 degrees, and the other side is also equal to the radius. So now we know that the chord of 60 degrees is equal to the radius. Unfortunately, this method doesn't work for every shape. In fact, surviving records show that the Greeks mainly used the chord of 90 degrees, 72 degrees, and 60 degrees. Or in other words, using a square, pentagon, and a hexagon. And the method for finding the chord length of 72 degrees involves the golden ratio, so I won't get into it in this video. But this method was very limited. However, it did provide some seed chord lengths that helped in the next two methods. The second idea came from a simple observation about circles. Say you have a known chord length. I'll use a chord of 60 degrees here. This method allowed astronomers to repeatedly halve angles and generate new chord lengths from ones they already knew. Here's how it works. You first bisect this triangle, or cut it in half, to put it simply. So a line from a point on the circumference all the way down to the center. Now you have two right triangles because the chord of 60 degrees and this vertical line here are perpendicular. But how does this help us find the chord of 30 degrees? Well, if you connect this point here to this point here, this line is the chord of 30 degrees. Because we cut this angle 60 degrees in half as well when we bisected that triangle. So this angle, little angle here, is 30 degrees. Now let me write this separately so it's easy to explain. This is this entire triangle just enlarged and cleaned up a little bit. We know that this angle is 30 degrees, this side, or this vertical length, is equal to the radius, and this entire length here is also equal to the radius, because point from circumference, point in the center of the circle. And this length here, this horizontal length, is actually r divided by 2, because we know the whole chord length of 60 degrees is equal to r, the radius, and if you cut it in half, you get, well, r divided by 2. Next, you have to find this length here, or the larger part of this entire length. And you can do this by using the Pythagorean theorem. We get root 3 on 2r for this large length here. So the small length must be r minus root 3 on 2r. And that simplifies to r times 1 minus root 3 on 2. To find the chord of 30 degrees, you have to use the Pythagorean theorem again. After a lot of algebra, we find that the chord of 30 degrees is equal to r times the square root of 2 minus the square root of 3. So using this method, we can just keep halving the angle or finding chord lengths for half our original angle. So we can go from 60 degrees to 30 to 15 to 7.5 and so on. And the same for 72 degrees and 90 degrees. But again, this is still a far cry from the chord length for any angle. By the time of Claudius Ptolemy, in the 2nd century AD, these geometric techniques were already part of the mathematical toolkit. Ptolemy combined them with a powerful new result, now known as Ptolemy's theorem, which relates the sides and diagonals of a quadrilateral inscribed in a circle. Using this relationship, he could compute chords of sums and differences of angles. But before we get to that, we need to look at Thales' theorem, or the interception theorem. If I have a triangle inscribed in a circle such that A and C are directly opposite each other, so the distance between them is equal to the diameter, and a point B that's anywhere on the circumference of the circle. Now, if I measure the angle at point B, I find that it's actually equal to 90 degrees. So a triangle formed such that A and C are 2 points, or directly opposite each other, and the third point's anywhere on the circle, that triangle will always be a right triangle. This theorem, combined with Ptolemy's theorem, which states that for any quadrilateral inscribed in a circle, so I'll take this point D here and just make a four-sided shape and another diagonal. If I multiply the lengths of these diagonals, so AC times BD, it's equal to the opposite sides multiplied together and added. So let me write it out. I'll take AB and multiply it with CD. So dot CD plus the side BC multiplied with AD. This is Ptolemy's theorem, and he used this to find the chord lengths of sums and differences of angles. But how? Say we want to find the chord length of 132 degrees. Well, 132 can be split into 72 and 60 degrees. So I would place those chords next to each other, like this. So I've labeled A as a chord of 60 degrees, or lowercase a as a chord of 60 degrees, and lowercase b as a chord of 72 degrees. And these two are known values, and I'll write that down so it'll make sense later. So we know the values of A and B. Now, I'll take a point here, directly opposite. So I can draw a straight line that's equal to the diameter straight across. And I can make a quadrilateral by connecting everything up. And I'll also connect these two vertices. And this length here is actually the chord of 132 degrees, because 60 plus 72 gives 132 degrees. But how can we find that? Well, let's start by labeling all the sides. I'll call this one here side C, this one side D, call this E, and finally our chord of 132 as F. Now, we know the length of E because it's equal to the diameter. So I'll write that down, E. But there's still three other unknowns. Since this length is a diameter, and this is any point on the circumference, this angle here is a right angle. So the triangle with side lengths A, D, and E is a right triangle. And likewise, the triangle B, E, and C is also a right triangle. And we know the values of B, A, and E. So using the Pythagorean theorem, we can find the values for C and D. Let me draw it out so it makes more sense. So these are the two triangles here. Ignore the side F, or the diagonal F. So we know A and E. We can find D using the Pythagorean theorem. And likewise, we know E and B, so we can find C. Now we know 5 sides, A, B, C, D, and E. And our only unknown is F. So here's where Ptolemy's theorem comes in. So we'll rewrite this like this. AC times BD becomes E times F because there are diagonals. AB times CD becomes A times C. A dot C plus BC times AD is B times D. Since we know A, B, C, D, and E, we only need to find F. And we can find that by moving E to the other side or dividing both sides by E. And since everything on the right is constant, then this is a full value. I'm not writing it out here because it'll get too messy. We've just found the chord length for 132 degrees. And we've also found the chord length for 120 degrees because this angle here is 120, and the chord length of 108 degrees, side C, along with the chord length of 132. So this is how Ptolemy was able to build a chord table with an increment of 0.5 degrees. Yes, this method is messy and calculationally intensive, but this helped astronomers track planets to within a half degree of precision. This was truly a feat for the time. In this video, we've gone over how we can find the chord lengths for almost any angle using, well, first, inscribing polygons, second, using angles from those polygons to find the chord lengths of half those angles, and finally, Thales' and Ptolemy's and Pythagoras' theorem to find the chord length for almost any angle. In part 2, we'll be going to ancient India to look at the works of a guy named Aryabhata. And while the Greeks were messing about with full chords, he was more focused on half chords. This concept of chords brings us one step closer to truly understanding what trigonometry is. So that's it for this video. Thanks for watching. I'll catch you in the next one.